Okay, this is problem 152. This problem deals with a hair dryer, and as you can see from the diagram here, air is drawn in by a fan into a cylindrical duct where the air is heated up by an electric coil and then is discharged out. And you can see that the temperature comes in at T sub I and it leaves at T sub O. So for part A in this problem, we're told that the power provided by the electric coil is 500 watts. The inlet temperature of the air is 20 degrees C. The discharge temperature or exit temperature is 45 degrees C. And so from this we need to determine what the volumetric flow rate V dot is. So we're going to start then by saying what is given. Well, what's given is the electric power is 500 watts. The inlet temperature is 20 degrees C. The discharge temperature is 45 degrees C. And if you look further in part A, you see that the duct has a diameter of 70 millimeters, which we'll keep everything in SI units, so we'll say 0.07 meters. And we're given that the density of the air is 1.10 kilograms per cubic meter, and the heat capacity of the air is 1007 joules per kilogram Kelvin. So the two things that they want you to find in part A of this problem are the V dot, the flow rate, as well as the discharge velocity, VO. So what you would do then is draw a diagram that pertains to the system, which we already have over here on the left. So what we'll do is draw a little box, a little control volume around the hair dryer here, and we'll replicate it down here to our energy balances. So what's coming in is we have the energy associated with the air coming in. We also have the energy associated with the air going out. And we have the electric power coming in. Now, one of the important things that they say in here is that the heat loss from the casing to the ambient air in the surroundings may be neglected. So when they say that, the heat loss then, they say to the ambient air around the hair dryer, it means that they're saying that there's a convective loss. And they say to the surroundings that implies that there's radiation. So we're going to assume, based off of this statement here, that since it's negligible, that this Q loss is going to be 0. So if you look at assumptions that we would employ here, the first one, of course, is that Q loss is 0. A second one that's important is that this whole thing implies that the system operates at steady state. Alright, the third one, if you look here, you have a fan. So we're going to assume then that the fan doesn't really play a major role as far as the energy balance goes. So we'll say that the fan doesn't have friction heating. In reality, no fan is 100% efficient. There is going to be a little bit of friction heating, but we're not going to worry about it here. It's going to be negligible compared to the heat provided by the electric coil. The last thing is that the fan itself does provide some influence on potential and kinetic energy. But if you look at this, you have a constant diameter duct, which means that the kinetic energy won't change. You'll learn about this in fluids class if you haven't done so yet. If the duct diameter is the same, there's no nozzle. And since there's no nozzle, there's no change in kinetic energy. And along the same lines, since the little hair dryer is listed as being horizontal, there shouldn't be any influence by potential energy either. So all the change in energy for the air is thermal. So let's now move on to the analysis then. So looking at our little diagram here, if we ignore Q loss, then we can say then that We write the first law, dECV dt is equal to E dot in minus E dot out plus E dot gen. There is steady state, so this first term goes off. There's no generation, so that's 0. And so therefore you're left then with E dot in minus E dot out equals 0. Alright, so E dot in, if you look at the diagram, is going to be comprised of E dot in air plus P electric. E dot out is going to be E dot O air. So now we can modify our equation again. So E dot in air plus P electric is equal to E dot out air. Now we need to know what the values are with this. Well, thermodynamically, the thermal energy associated with the air energy coming in is going to be m dot C sub P T sub I. That going out is going to be m dot C sub P T sub O. So we're not given m dot in the problem explicitly, so this m dot then we can find fairly easily is rho times v dot. So what we can do then is we can rewrite this equation and combine some terms together. What we get then is rho v dot C sub P To minus Ti is equal to P electric. Or we get our answer in terms of just the parameters, but not the numerical values. V dot is P electric over rho C sub P To minus Ti. So let's plug in some numbers. P electric we know is 500 watts. Rho is 1.10 kilograms per cubic meter. C sub P is 1007 joules per kilogram Kelvin. To is 45 degrees C. Ti is 20 degrees C. Now, if you look at this, one thing you always want to do is look at the units and make sure that makes sense. So, a watt is a joule per second. So then the joules will cancel out from the numerator and the denominator. The kilograms right here will cancel out the kilograms here. So you can see that if you have an extra per second, then you're going to have a meters cubed per second, but you still have this Kelvin right here, and you have a degree C right here. When you have a temperature difference, is that it turns out since degree C and Kelvin have the same magnitude when you look at a difference in temperature, right? So again, a Kelvin is a degree C plus 273.15 degrees. So what we can say, because we have a temperature difference, and replace that the degree C with a Kelvin. So this is okay because of the fact that we have a temperature difference. So if we do the math, what we end up getting then out of this is 0.0181 cubic meters per second. So we have to draw a box around that. So that's the first part of the problem. Now the second part, we want to look at what the outlet discharge velocity is. And that's fairly simple to find. It is V dot over the cross-sectional area A sub C. A sub C is going to be equal then to pi over 4 d squared. So if we plug that into our equation here, it's 4 v dot over pi d squared. So we write in our numbers here. 4, we're going to have 0.0181 cubic meters per second over pi times 0.07 meters quantity squared. If you notice here, the units then work out to be meters per second, which is what we'd expect for speed. And we get a value then of 4.70 meters per second. Now what you want to do when you look at these problems is you want to make sure if the numbers make sense. So one thing we'll do, as a little bit of a bonus here, is we'll take a look here and make sure these make sense. So this value of 0.0181 meters cubed per second, if we were to put in a Wolfram Alpha and do a unit conversion, this is roughly around 40 CFM, which is a good number, because that 40 CFM is about typical for a small fan. 4.70 meters per second, if you put it in and do a unit conversion, is roughly about 10 miles per hour. Again, a breeze of 10 miles per hour, it seems plausible for a hairdryer. So these numbers seem to be realistic, so that gives a little bit of validation that we're doing things appropriately. So that's for part A. For part B, we're going to take this dryer, we're going to provide it a length of 150 millimeters, and we have a surface emissivity of 0.8. Whenever you see an emissivity provided, this should tell you right away that there's radiation going on. Then it says if the coefficient associated with the heat transfer by natural convection from the casing to the ambient air is 4 watts per meter squared Kelvin, and the temperature of the air and the surroundings are both 20 degrees C, confirm that the heat loss from the casing is in fact negligible. The casing may be assumed to have an average surface temperature of 40 degrees C. So for part B now, what we're given is a length, 0.15 meters, heat transfer coefficient of 4 watts per meter squared Kelvin, which is a typical value you'd see in natural convection. And we're given that the surrounding air and the surrounding environment, both at 20 degrees C, or if you want to put it in terms of Kelvin, it's 293 Kelvin. Finally, the surface temperature is 40 degrees C, or 313 Kelvin. We want to find then Q loss. So the diagram we have back up top says that Q loss is the part due to convection and the part due to radiation. So this Q loss then is Q convection plus Q radiation. So convection, we know, is going to be H times the area, which will be the outer surface area of the cylinder, and it'll be Ts minus T infinity, whereas radiation, you're going to have the surface area times sigma times epsilon times Ts to the fourth minus T surroundings to the fourth. So let's go ahead and put that in. Is going to be H AS Ts minus T infinity plus AS sigma epsilon Ts to the fourth minus T surroundings to the fourth. So the only thing we need is A sub S, which is, since we're dealing with the sides of a cylinder, it's going to be pi times D times L. So put it in for both of those spots right there. So what we get then is Q loss is H pi dl Ts minus T infinity plus pi dl sigma epsilon Ts to the fourth minus T surroundings to the fourth. So this is the answer in terms of parameters. We can determine what it is numerically. Plug again 4 watts per meter squared Kelvin times pi times 0.07 meters times 0.15 meters times 40 degrees C minus 20 degrees C. And again, since we're dealing with a temperature difference, or take that degree C and convert it to Kelvin, and then you add the radiation term, pi 0.07 meters times 0.15 meters times sigma, which is 5.67 times 10 to the minus 8 watts per meter squared, Kelvin to the fourth, times epsilon, which is 0.8, times the surface temperature, and you have to use absolute units here, so it would be 313 Kelvin to the fourth, minus the surroundings in absolute units, 293 Kelvin to the fourth. And putting them together, you get the convection term is 2.64 watts and the radiation term is 3.33 watts, so you get a total then of about 5.97 watts. So this is the numerical value you get from part B, but what they're asking is, can you show that the assumption that Q loss is very small, is that valid? And we can do that, because we know that Q loss now is approximately equal to about 6 watts. And we're comparing that to the electrical power you're putting in, which is 500 watts. And since Q loss is much, much less than P electric, then the assumption that Q loss is negligible, you can set it equal to 0. It is indeed valid. So that's essentially how you would solve problem 52.